Hey everyone, so we already talked about current and circuits, and we talked a little bit about the introduction and basics. So I just wanted to mention a few other things about current and circuits. Now, that you should have learned a little bit about the object of the concept of resistance. The important thing is uh, there are objects that typically have low resistance that allow for a very easy flow of current and for charges to go through them. We normally call these objects conductors. And these are things like metals and ionized liquids and gases. Because the reason why these objects in particular are really good at allowing for current to flow is that they have a very loose connection to their electrons. Metals, for example, typically have, like I said, loose connections with their electrons. They have free flowing electrons that are constantly just moving around between the atoms. Ionized liquids and gases, well, while they don't have free flowing electrons, they are by themselves charged, so they will allow for electrons to move one way or another. On the flip side, though, if an object has a very high resistance, that basically means that it's going to try to resist current from flowing as much as possible. So it makes it really hard for electrons to flow. And we usually call these objects insulators. These are things like rubber, glass, wood, and like I said, just similar to the metals where instead of having a loose connection to their electrons, they usually have a very tight hold on their electrons and they don't really allow for charges to move. Now, it's important to note that when we say that an object is an insulator and that it has a high resistance, that it resists current from flowing, that doesn't necessarily mean that current will never flow. If you end up having a high enough potential difference, current will always end up moving eventually. It just means that it requires a whole lot more effort to get charges to flow through wood than it would through metal. All right, now here's a question I want you to try to think about. So pause the video, work itself, and we'll go over in a second. Now the question is pure water a good conductor of electricity? Well, this seems like the answer should be yes, because as you may know, if you try to go into a bathtub with a toaster oven and you have the toaster oven running and a TV running too, and all of a sudden they fall into the bathtub, it's not good. You end up having a very bad day. So it would be clear to say that obviously water should be a good conductor of electricity. However, there's a key term here, pure water. There's a difference between pure water and the water that we normally experience, like being in a pool, in the ocean, in a bathtub. And that's the fact that in those waters, there's usually ionized particles in there, salts, especially in the bathtub. When you go in there, you have all these oils and salts in your body that end up coming off and basically becoming ionized within the water. Water is actually really good at ionizing particles and breaking them up. So, for the most part, if you have very pure water that doesn't have any contaminants and it doesn't have anything to break down to create these ionized particles, it turns out that it's actually a really bad conductor. You can actually test this yourself. Even though water from the tap isn't really considered pure, you can actually, I mean, if you have the materials, obviously, but what you can do is actually take wires, connect them to a battery, and then connecting it to a light bulb, have the wires kind of open within the water, and you'll see that the light bulb doesn't turn on. But once you start adding some salt and start spinning it around, all of a sudden those ionized salt particles will allow for the light bulb to turn because now it becomes a conductive material. So one of the things that we need to talk about is the idea of resistance. So objects usually resist current, and depending on how the object is made and the materials, it will affect the current flow differently. Now, in particular, the one thing that we're going to focus on is wires. Now, one thing that we need to know is that wires do have a relationship to temperature and how that affects its resistance. As it turns out, as the temperature increases, the resistance will also increase. Now, here's just a simulation on pretty much what a resistance wire will look like. So if we have a wire piece of material like this, its resistance value, this R term, is going to be related to these three variables, in addition to temperature, of course. This symbol, the rho, is representing the resistivity, L is representing the length, and A is representing the area. Now, you can see over here that I can adjust these sliders, and that's going to affect the resistivity. If I increase this, you can see that it starts adding in a bunch more charges. With the added materials inside this wire, it now is going to make it harder for electrons to flow through because they're going to be constantly bumping into these particles, making its resistance higher. If I lower it, all of a sudden these obstacles start getting smaller and smaller, and there's not as many. Now it's going to be a lot easier for electrons to flow through and be able to go in between these particles without really bumping into too many. So the higher the resistivity, the harder it is for electrons to flow through. The lower resistivity, the easier. And we could see it in here by the fact that as this goes up, this goes up. As this goes down, this one goes down. So they have what we call a direct relationship. Similar thing with the length, we can see is that if we increase the length, that increases the resistance. Again, that kind of makes sense because if the electron's flowing through here, now that the wire's a lot longer, it's going to take a lot more time for it to go through than if the wire was only very short. Imagine you're making a race, you're running a race, and you had to choose between a stretch of track that was covered in mud that was really long versus really small. So you can see there that the longer that slowed down section is, the harder it is for you to follow through. And once again, length and resistance have a direct relationship. And then the last one's the area. So here you'll notice that as I increase the area, it actually ends up decreasing the resistance. And because of this, it's allowing for more charges to flow through as they travel in the area. And if I decrease, I actually increase resistance very high. So these two variables have an inverse relationship. So between these variables, resistivity, length, area, and temperature, you really need to know how changing one is going to affect the other. Now the good thing is that you have the equation on hand in order to actually deal with this. However, with the exception of temperature, that's one that you have to memorize. But sometimes it's really helpful to kind of try to come up with some sort of an analogy that will help you kind of remember the concept even more, especially at the when you're taking the test. Now, the analogy that I always think of is I think of a wire as being like a hallway, because that's something that we all experience in our everyday life, and the resistance in this case is how hard it is for you to move through. If it's really hard for you to move through the hallway, that hallway has a high resistance. If it's easy, then it has a low resistance. So R is how hard it is to move through. We have rho, which is the number of annoying, slow moving people within that hallway. L is the length of the hallway. A is the width of the hallway. And the temperature is the random chaotic speed of these annoying kids. So if you try to visualize, it makes sense how changing these would affect the resistance. As we said, rho being related to the number of people, you can imagine that if you had to go through a hallway that had a ton of people, where the people were packed together, it would be really hard to make it through there if no one else is moving. Likewise, or on the flip side, if the hallway was completely empty, it would be extremely easy for you to go through. So the higher the resistivity, the higher the resistance. Same thing with the L. If there's a stretch of hallway where there's a lot of people, then that's going to be a lot harder to get through than if the path you had to travel was only like a few feet. A is related to the width, so this one kind of might help out in the other case. If you can imagine a hallway where you have the hallway being really, really wide, it'll allow you for more room to move between the people. But if instead the hallway was kind of condensed so only one person can fit through at a time, it being packed with people would make it extremely hard, since it would take a lot of effort to go around the people or over the people in that really packed tiny hallway. And then the temperature, the chaotic speed, with them constantly bumping into you, it again makes it super hard for you to walk through. So this could be a useful analogy to kind of remember it on the day of tests, because like I said, it is going to be important that you're going to have to pull it out and know, okay, if I change the temperature, how's that going to affect the resistance? If I change the area, how's that going to affect the resistance? All right, so here's the next question. Pause video, work yourself, and we'll go over in a second. All right, so one of the main things to realize is we're going to start making circuits, and when we make circuits, we want to make sure that the wires that we use that connect all the devices have the smallest possible resistance. So what type of material should it be made of? Well, if we want the smallest resistance, the material, the resistivity, should be the smallest resistivity. So if you look on the front of the reference, not the front, but if you look on the resistivity table on the reference table in the electrostatics section, you'll see that silver is the one with the lowest resistivity. So silver would be ideal for wires. However, it's actually interesting to note that in the case of real life, silver actually isn't the best wire to use. Some of you may have thought that gold is better, but if you look at the resistivity, gold is actually a little bit higher than silver. So why is gold usually considered better? Well, if you think about how those materials actually interact, silver tends to get very corroded easily and oxidizes easily. So even though it's really good resistivity wise and has a very low resistance, it tends to get messed up, and it would be something that we'd have to kind of constantly change out. But with gold, it has a lot higher durability. So typically we actually go with gold, even though we kind of lose a little bit on the resistance side. It makes up for its long lifespan. Part B, the dimensions of the wire. Should it be short or long, thick or thin? Well, again, if we want the smallest possible resistance, we're going to want it to be as short as possible and as thick as possible. So we want it short and thick to, again, allow for as much electrons to be able to pass through as quickly as possible. All right, so that's it for this part. We just finished talking about the whole idea about resistance and some of the factors. We're going to keep talking about some other things like with circuits and different types of circuits. If you have any questions or concerns, either join the extra help or you can message me on Remind. Besides that, good luck and have a great day.